Welcome back to the module on dynamic approaches for automated machine learning. In this unit, we're going to take a look at reinforcement learning as it's the required background for the remainder of this module. Now, the goal in reinforcement learning is that an agent learns how to behave in an environment by maximizing a reward. So to this end, we have an agent and an environment, and the agent can observe the state of the environment. Based on this observation, the agent reacts with an action which induces some change in the environment, and with this change, the environment produces a new state and emits a reward signal. Now, this is all that we need to learn how to maximize a reward and reinforce good behavior and learn to avoid bad behaviors. You will also often hear people talk about policies in reinforcement learning. And the difference between a policy and the agent is that the policy is the entity that maps the observation to a desired action, whereas the agent is the overall decision-making entity. Right, so it contains the policy, but it's more than just the policy. So you want to tune the hyperparameters of your agent to learn a better policy. You might now ask yourself, what even is a state? And to give you some idea of what we humans would say a state is, we can sense what is going around. So we have some images that we observe. We hear something. We feel the touch of surfaces. We feel if we're being accelerated, if we're sitting in a car or in a train, and we have a certain sense of balance, right? So all of these senses are part of our state, of our observations that are happening. So for the sake of this lecture, we will talk about the state being something that is observable, and we will not take into account that there is the notion of partial observability in Markov decision processes and so on. But for those of you that are interested in it, here is also a very interesting reference for you to check out. Now, actions as part of the reinforcement learning will induce some change in the environment. All right, and we have different types of actions. Continuous ones are usually constrained by a certain range, and we often have the range set to the 0-1 domain, especially since we're using deep reinforcement learning or deep neural networks, and 0-1 is a good area for optimization. Right? Now, examples from robotics include you want to control some velocities or angles or probabilities, and in video game playing, right, the controller inputs are classical actions that you want to take. And in AutoML, we have had the learning rates as a running example going on. Now, we also can have discrete action choices where we choose from a set of possible actions. And in robotics, that could mean you run some subroutine that you just follow for a while, or you trigger some interrupts which give you a discrete event that is happening. Video game playing, the pendant to controller inputs are keyboard inputs where you just have discrete button presses rather than these continuous joystick operations. And in AutoML, you could think of mutation operators or some heuristics that you select and apply for a step or even multiple steps. Now, transitions are a very important concept for reinforcement learning because if we are in a certain state and we want to play a certain action, the question is, which is the state that we end up in? And that is determined by the transition dynamics in an MDP. Now, this could be either deterministic or non-deterministic. Most often, board games are deterministic. Such board games could include Go or chess. But there are also obviously games with randomized events, such as card games. And coming back to the robotics as an example, the controllable robot is not perfect, right? If you tell the robot to move the arm to a certain angle, it might not be perfect and it might overshoot slightly or undershoot slightly. So you do not have perfect control of a system always. If the state is non-deterministic, it's very important that you also take into account that you have these different types of uncertainty attached here. For example, if the action was responsible for the stochasticity, that is the epistemic uncertainty, which you can potentially control. Whereas if it's inherent to the environment, the aleatoric uncertainty, you do not have direct control over this. And stochastic environments are much more challenging since you really need to account for this different notion of reproducibility, right? You need to understand if you are in a certain state and if you play a certain action, will you get into a next state that is close enough to the previous next state where you learned that the actual action that you took to get to this state was a good choice or not. But important, right, for reinforcement learning, we do not need access to the transition function. We do not need to know it in order to learn well-performing policies. And we will see an example of not having access to the transition function in the remainder of this unit. Now, rewards are really crucial for reinforcement learning as they provide the feedback that we need to learn. And rewards can be dense, being immediately present, or sparse, right? And if we have a dense reward, it's easier to learn from than a sparse reward because we have to wait for some states to observe the outcome of a previous choice with the sparse reward. So it's a little bit more difficult, or oftentimes much more difficult, to actually learn from sparse rewards. We need to balance the reasoning about the immediate gratification versus long-term ramification. So this temporal credit assignment is really, really difficult, and it's one of the big challenges in reinforcement learning, where you will find various different approaches of how to deal with it. But here in this lecture, we will not take care of this. Now, I want you to recall that machine learning was introduced as an iterative process in one of the earlier units. And I want to give you the insight that reinforcement learning is also iterative, right? But there's a crucial difference, right? So we start with an initial agent, which is similar to the initialization of the model, but we do not have the data present immediately. We start from a random policy potentially, and we first need to generate our own data to learn from. Once we have generated some data, we can compute a loss based on which we update the agent or the policy, and then we generate some new data, right? So we repeat these steps of generating new data to learn from over and over again. Now, most RL agents actually aim to estimate the so-called value function or state action value function. And this value function tells us how valuable it is to be in a certain state, or how valuable it is to be in a certain state and play a certain action in the state, with the expectation of this future rewards that we might be getting. And these value-based algorithms directly use the estimate to derive a policy. And Q-learning here that we're going to talk about is one of the most famous examples. So this is the overall Q-learning formula. It might look a little bit daunting, but actually it's nothing not so different than supervised updates that you might be used to, because here is the old estimate, and we update it with a learning rate given some expectation or like gradient signal, should we move more in a certain direction or not. But let's talk about this in a little bit more zoomed in fashion. So let's first look at the so-called temporal difference target. This temporal difference target is the sum of the immediately observed reward and the expected future rewards that we get by behaving greedy with respect to the current Q estimate. Right? So we know we end up in the next state, and now we want to behave maximally greedy with respect to this. And this gamma here, this discounting factor, weighs how much we expect that future rewards should matter for this overall estimation of this temporal difference target. Now the TD delta then is nothing else than the difference between the predicted future reward plus the observed immediate reward and the old estimate of the future rewards that we will be getting, right? So in deep learning or supervised learning terms, the TD target defines the regression value, and the TD delta defines the prediction error. And then we use a learning rate to update our old estimate with respect to this estimation error, right? So this really determines how strongly we update this. And this is one of the most famous and one of the most used reinforcement learning algorithms still to date. Now, once you have this Q value, actually getting your policy is super straightforward, because all you need to do is behave maximally at every state that you have, that you observe. And there's a very nice theory about this, showing that this is actually getting you to the optimal policy over time. But again, I would leave this research or the literature research to the interested audience members. What I want you to take home is that reinforcement learning agents generate their data while learning. So this introduces a stronger non-stationarity than supervised learning, and reinforcement learning thus is a prime candidate for actually using dynamic algorithm configuration methods themselves. So you have often seen in the literature that PBT is applied to reinforcement learning. Q-learning estimates how good it is to traverse through a state, right? We know the value of being in a state and playing a certain action, so traversing through it, and the policies are trained to maximize future expected rewards.